What if everything we thought we knew about time was just the beginning? Picture this, not as a steady, unchanging force, but as something far more mysterious, a boundary that bends, twists, and even flickers at the very edges of our universe. For centuries, humans have tried to pin down time, from the shadow of a sundial to the precise tick of an atomic clock. But what if the true nature of time isn't just about counting seconds? What if it's a cosmic frontier waiting to be explored? This is the story of the discovery that shattered our old ways of measuring time and opened doors to a new understanding of reality itself. It wasn't just a breakthrough in physics or astronomy. It was a revolution in how we see the universe. The scientists behind this revelation didn't just change textbooks. They rewrote the rules of existence, revealing that time isn't a rigid line but a fluid, dynamic force intertwined with the fabric of space. And the implications, they're as vast as the cosmos, touching everything from black holes to the very origins of reality. So how did we get here? The journey spans millennia, from ancient civilizations tracking the sun's path to modern labs where atoms dance to the rhythm of quantum mechanics. Along the way, there were moments of brilliance, stubborn mysteries, and experiments so daring they pushed the limits of human imagination. And now we stand at the edge of a new frontier where time itself might hold secrets we've only begun to glimpse. Buckle up, because this isn't just a history lesson, it's an invitation to witness one of the greatest leaps in science, a discovery that redefined not just how we measure time, but how we measure our place in the universe. Long before we split seconds into billionths or synchronized global networks with atomic precision, time was measured by the grand motions of the heavens. Ancient Egyptians didn't just watch the sun, they built towering obelisks whose stretching shadows became the world's first clock hands, marking hours with nothing but geometry and light. Meanwhile, Babylonian astronomers mapped the stars with such precision they could predict eclipses centuries in advance, weaving timekeeping into the very fabric of their myths and agriculture. These weren't just practical tools, they were acts of reverence, attempts to touch something eternal. But perhaps the most ingenious were the water clocks of ancient China and Greece, vessels that dripped at a steady pace, turning the flow of a river into a measurable rhythm. Imagine the leap this represented, no longer relying solely on the sky's whims, but harnessing Earth's own elements to tame time. These cultures understood something profound, that time wasn't just a backdrop to life, but a force as tangible as the Nile's floods or the harvest moon. What's striking isn't just their creativity, but the universality of their obsession. From Stonehenge's solstice alignments to the Mayans' intricate calendars, civilizations separated by oceans arrived at the same realization, that tracking time meant unlocking order from chaos. They laid the foundation for every clock, every equation that followed, proving that humanity's relationship with time has always been part science, part poetry. And buried in their stargazing and sundials was a quiet question we're still answering today. Is time something we measure, or something we're woven into? The ticking of medieval clocks might seem quaint today, but those intricate gears represented a revolution, the moment humanity first wrestled time into a mechanical embrace. Picture the scene, towering cathedral clocks in 14th century Europe, their iron hands slicing daylight into equal hours for the very first time. No longer bound by the sun's arc or the moon's phases, people could now share synchronized moments across towns and trades. Yet for all their ingenuity, these early clocks drifted by minutes a day, their rhythms swayed by temperature, friction, even the wear of their own parts. The real breakthrough came when we stopped measuring time by the swing of a pendulum and started listening to the hum of atoms themselves. In the mid-20th century, scientists discovered something astonishing. Cesium atoms vibrated at a staggeringly precise frequency when exposed to microwaves exactly 9,192,631,770 times per second. This wasn't just accurate, it was universal. Unlike pendulums or springs, atoms didn't slow down in humidity or speed up in heat. They danced to a rhythm written into the fabric of reality, giving birth to atomic clocks so precise they'd lose less than a second in millions of years. But here's the twist: even as these marvels synchronized global navigation and digital networks, they revealed a deeper mystery. When physicists compared atomic clocks on Earth to those aboard high-speed jets or satellites, something bizarre happened. The clocks in motion ticked slower, just as Einstein's theory of relativity had predicted decades earlier. Time itself wasn't the rigid constant we'd imagined. It stretched and compressed like taffy under gravity's pull or at extreme velocities. Suddenly, the quest to measure time became a window into the universe's most profound secrets, proof that time and space were woven together in a cosmic tapestry where black holes could slow it to a crawl, and the Big Bang might have been its very beginning. This was the revelation that changed everything. Precision timekeeping wasn't just about counting seconds anymore. It was a compass pointing toward the hidden architecture of existence. And the deeper we looked, the clearer it became. To understand time, we'd need to rethink reality itself. Einstein's theory of relativity didn't just tweak our understanding of time, it upended it completely. Imagine standing next to a massive object like a black hole, where gravity is so intense that time doesn't just slow down, it practically crawls. A single hour for you might stretch into years for someone far away in the cosmos. This wasn't science fiction, it was the universe revealing its rulebook. Einstein showed us that time isn't a rigid, unchanging backdrop but a flexible fabric, warped by gravity and motion. Yet for all its brilliance, relativity left a puzzle hanging in the air. If time bends so dramatically under extreme conditions, how do we pin it down? How do we measure something that refuses to stay constant? The answer lay in the strange, counterintuitive world of quantum mechanics, a realm where particles can be in two places at once and where reality itself seems to flicker like a candle in the wind. At first glance, relativity and quantum mechanics couldn't be more different. One deals with the vast, smooth curves of space and time, while the other thrives on the jittery, unpredictable behavior of the tiniest particles. But hidden in their contradictions was the key to unlocking time's deepest secrets. Scientists realized that to measure time at the edge of reality, where black holes lurk and the universe began, they'd need to bridge these two theories. This wasn't just a technical challenge, it was a philosophical earthquake. For decades, physicists wrestled with the implications. If time could stretch and compress, what did that mean for the moments we consider fixed? The ticking of a clock, the aging of a star, even the lifespan of the universe itself. The quest to solve this riddle led to some of the most daring experiments in history, from atomic clocks placed on speeding jets to satellites orbiting Earth, each one confirming Einstein's predictions while opening new questions. What emerged was a revelation. Time isn't just elastic, it's layered, with different rules operating at different scales. Near a black hole, relativity reigns supreme, warping time into a slow-motion dream. But in the quantum realm, time might not even flow in a straight line. Some theories suggest it could loop, stutter, or even exist in fragments. The discovery that changed how we measure time wasn't just about building better clocks. It was about realizing that time itself is a mosaic, pieced together from the interplay of the infinitely large and the vanishingly small. And that realization, it's still reshaping our understanding of everything from the birth of the cosmos to the fate of reality itself. If superposition bends the rules of reality, what does that mean for time itself? At the quantum scale, particles don't just obey the steady tick of a clock. They exist in a haze of possibilities, flickering between states like a light switch that's both on and off simultaneously. This isn't just theoretical weirdness, it's a fundamental challenge to how we perceive time's flow. Imagine a single electron orbiting an atom. Until measured, it isn't in one place at one moment, it's everywhere it could be at once, as if time itself hesitates to pin it down. This ambiguity led physicists to a radical idea. If particles can defy classical physics, maybe time does too. Experiments with entangled particles, where changing one instantly affects another, no matter the distance, hinted that time might not always move forward in a straight line. In certain quantum systems, cause and effect can blur, with events appearing to influence each other backward or sideways through time. Picture a game of pool where the balls decide their own paths after they've already landed in the pockets. The real shock came when researchers explored quantum clocks, devices that measure time using the oscillations of atoms trapped in superposition. Unlike traditional clocks, these didn't just count seconds, they revealed time's fragility. In one groundbreaking experiment, scientists observed that a clock in a quantum superposition of two states actually ticked at two different rates simultaneously. It was as if time itself had split into parallel threads, each flowing at its own pace. These discoveries didn't just complicate timekeeping, they forced us to confront whether time's edge is a sharp line or a shimmering frontier. Some theories now suggest that at the smallest scales, time might loop like a Möbius strip, or even emerge from something deeper, a cosmic code we're only beginning to decipher. The quest to measure time has become a journey into the heart of existence, where every tick of the clock might be rewriting the rules of reality. Black holes aren't just cosmic vacuum cleaners, they're time machines in disguise. Their gravitational grip is so overpowering that near the event horizon, the boundary beyond which nothing escapes, time doesn't just slow down, it grinds to a near halt. Picture an astronaut falling toward a black hole, their signals back to Earth stretching into longer and longer intervals until, from our perspective, they appear frozen in time. Yet for the astronaut, seconds pass normally, a paradox that reveals time's shocking flexibility. This extreme distortion isn't just a curiosity, it's a laboratory for testing the limits of physics itself. For decades, scientists saw black holes as the ultimate proving ground for Einstein's relativity. But the real breakthrough came when they realized these cosmic anomalies might also hold the key to reconciling relativity with the quantum world. At the heart of a black hole lies a singularity, a point where gravity becomes infinite and the laws of physics as we know them break down. Here, time and space cease to behave in ways we can comprehend. Theorists began to wonder, if black holes warp time to such extremes, could they also reveal how time emerges from the quantum foam at reality's smallest scales? The answer came from an unexpected place: black hole thermodynamics. In the 1970s, physicist Stephen Hawking made a startling prediction that black holes aren't completely black. They emit faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. This discovery bridged relativity and quantum mechanics in a way no one had imagined, showing that even the most extreme gravitational environments are subject to quantum rules. But the implications went deeper. Hawking radiation suggested that black holes slowly evaporate over time, raising profound questions about what happens to the information and the flow of time trapped inside them. This paradox forced physicists to rethink time's fundamental nature. If information can't be destroyed, as quantum mechanics insists, then time inside a black hole might not simply vanish, it could be encoded in some exotic form, like a cosmic hard drive. Some theories now propose that black holes don't erase time but transform it, twisting it into a holographic projection on their surfaces. Others suggest that the event horizon acts like a quantum clock, its fluctuations marking time in a way that blends relativity's smooth curvature with quantum mechanics' jittery uncertainty. The most revolutionary idea, that black holes might not be the end of time but a window into its true structure. By studying how time fractures at their edges, scientists are uncovering clues about how it behaves everywhere, from the birth of the universe to the quantum vibrations of atoms. Black holes have become more than cosmic oddities. They're the Rosetta Stone for decoding time's deepest mysteries, proving that to measure time, we must first understand the places where it nearly stops. The experiment that changed our understanding of time wasn't just precise, it was poetic in its simplicity. Scientists placed two atomic clocks side by side, but with a crucial difference. One sat slightly higher than the other, experiencing a fractionally weaker gravitational pull. According to Einstein, the lower clock, closer to Earth's mass, should tick slower, and it did. But then something extraordinary happened. When the clocks reached a level of precision beyond anything previously attempted, the data revealed tiny, flickering irregularities, like static on a radio tuned to the universe itself. These weren't errors in measurement. They were glimpses of time's hidden architecture, suggesting that at the smallest scales, time might not be smooth and continuous, but made up of discrete, indivisible units like grains of sand in an hourglass. This granularity would mean that time, like matter or energy, has a fundamental building block. Imagine zooming in on a digital photo until you see the pixels. This experiment hinted that time itself might pixelate at the quantum level. The implications ripple across physics. If time is granular, then the seamless flow we experience in everyday life is an illusion, a cosmic sleight of hand where reality refreshes itself in vanishingly small increments. Some theorists even speculate that these time pixels could explain why quantum particles behave so strangely, as if they're hopping between frames in an invisible film. But the real mystery lies in what this means for the nature of reality. If time has a smallest possible unit, does the universe operate like a quantum computer, processing existence in discrete steps? Could there be a frame rate to the cosmos, where each tick of this deeper clock updates the entire fabric of space-time? The experiment didn't just confirm Einstein, it opened a door to questions we're only beginning to ask. And as researchers push atomic clocks to even greater precision, they're not just measuring time anymore. They're decoding the universe's operating system, one quantum fluctuation at a time. Quantum clocks don't just measure time, they expose its hidden scaffolding. Where traditional atomic clocks paint time as an unbroken river, quantum clocks reveal something far stranger. A stuttering, stop-motion universe where time might advance in tiny, indivisible hops. Picture a flipbook animation where the pages turn too quickly for our eyes to detect the gaps between frames. That's the startling implication of these devices, that beneath time's smooth surface lies a granular structure, a fundamental pixel of reality some theorists call the chronon. This wasn't just a minor tweak to physics. It overturned centuries of assumption that time flows continuously, like an endless roll of film. Instead, quantum clocks suggested time operates more like a digital display, refreshing in discrete packets so brief, around 10 to the minus 43 seconds, that our intuition can't grasp them. In this view, what we experience as the steady march of seconds is really a cosmic illusion, the blur of reality updating itself trillions upon trillions of times per second. The evidence came from observing atoms in superposition. When scientists trapped ions in electromagnetic fields and watched their energy states oscillate, they noticed something bizarre. The transitions between energy levels didn't happen gradually. They occurred in sudden jumps, as if the atoms were clicking between predefined rungs on an invisible ladder. Each jump marked a discrete tick of the quantum clock, implying that time itself might advance in similar increments. Here's where it gets truly mind-bending. If time has a smallest possible unit, then concepts like the present moment take on new meaning. There can be no duration shorter than a chronon, no infinitesimal slice of now. This challenges our deepest intuitions about cause and effect. How can one event lead to another if time isn't perfectly continuous? Some interpretations suggest that at these scales, reality might process relationships between events probabilistically, like a cosmic roll of dice deciding what happens next. The implications ripple outward. If time is granular, then black holes' event horizons, where time appears to freeze from an outsider's perspective, might not be smooth surfaces but shimmering mosaics of quantum uncertainty. The Big Bang's first moments wouldn't be an infinitely dense point, but a rapid-fire sequence of time's fundamental units flickering into existence. Even our perception of free will comes into question. If the universe updates in discrete steps, are our choices made in the gaps between chronons? Yet for all its strangeness, this granular nature might explain why quantum particles behave so erratically. Their seemingly random jumps between states could reflect the underlying pulse of time itself, like dancers moving to the beat of a drum too fast for us to hear. Experiments now aim to test this by comparing quantum clocks in different gravitational fields. If time's graininess changes near a black hole's immense gravity, it would reveal an even deeper connection between quantum mechanics and relativity. What emerges isn't just a new way to measure time, but a radical reimagining of reality's fabric. The edge of time isn't a clean line where existence begins and ends. It's a frothing quantum foam where cause and effect tangle, where the universe might literally reboot itself with each passing chronon. And the most humbling realization that our perception of time's flow, the steady tick that structures our lives, is but a shadow cast by processes far richer and stranger than we ever dreamed. What if time isn't woven into the universe's fabric, but projected onto it like shadows dancing on a cave wall? This is the mind-bending premise of the holographic principle, a theory so radical it redefines reality's very structure. Imagine the entire cosmos as a cosmic projector screen, with every event, every particle, even the flow of time itself, encoded on a distant two-dimensional boundary. The three-dimensional world we experience, the stars, the planets, the ticking of clocks, would be nothing more than a holographic illusion, a slice of information rendered in real time from that edge. The roots of this idea trace back to black holes. When physicists calculated the maximum information a black hole could contain, they stumbled on something extraordinary. The data didn't fill its volume but was somehow painted onto its event horizon like a celestial hard drive. If a black hole's interior could be described entirely by its surface, why not the universe? The holographic principle takes this logic cosmic, suggesting that the entirety of space-time, including time's arrow, might emerge from interactions on a boundary we can't see. Here's where time gets truly strange. In this framework, the steady march of seconds we perceive could be a side effect of quantum entanglement, the invisible threads linking particles across vast distances. Just as a movie creates the illusion of motion from still frames, entangled quantum states on the holographic boundary might generate time's flow through their ceaseless interactions. It's as if the universe is running on quantum Wi-Fi, with time as the signal glitching into existence. Experiments are already probing this wild idea. Quantum computers simulate holographic universes in their qubits, revealing patterns that mirror gravitational effects, a hint that space and time might indeed be emergent. Meanwhile, physicists scrutinize the cosmic microwave background, the afterglow of the Big Bang, for anomalies that could betray the universe's pixelated underpinnings. If they're right, time isn't just something we measure. It's a collective hallucination, a story the universe tells itself to make sense of the quantum code beneath. The implications ripple through every facet of physics. If time emerges from a hologram, then black holes aren't just cosmic oddities. They're windows into the projection mechanism. The Big Bang might not be the beginning of time, but the moment the universe buffered into existence, even our free will could hang in the balance. Are our choices real, or just predetermined pixels on the cosmic screen? The holographic principle doesn't just challenge how we measure time's edge. It asks whether time exists at all outside the stories we tell about it. Time crystals sound like something ripped from a science fiction novel, structures that don't just exist in space, but pulse in time itself. Unlike ordinary crystals, where atoms arrange in repeating patterns like a diamond's lattice, time crystals flip the script. Their atoms oscillate in a never-ending dance, ticking like a clock with no battery, no energy input, yet never winding down. When scientists first synthesized these bizarre materials in 2016, it wasn't just a breakthrough in physics. It was like discovering a new law of nature, one where time isn't just a backdrop but an active participant in the fabric of reality. The magic lies in their defiance of equilibrium. Normal systems, when left alone, settle into a quiet, unchanging state. Think of a cup of coffee cooling to room temperature. But time crystals break this rule. Hit them with a laser or magnetic pulse, and their atoms don't just react once. They keep rocking back and forth indefinitely, locked in a rhythm that repeats not just in space, but in time. It's as if you plucked a guitar string and it kept vibrating forever, never losing energy to friction or air. This isn't perpetual motion, it's something far stranger, a quantum dance where the universe itself seems to bend the rules. What makes time crystals so revolutionary isn't just their weirdness, it's what they reveal about time's quantum origins. At their core, these structures thrive on entanglement, the spooky connection that links particles across distances. Each atom in the crystal doesn't just move on its own, it's choreographed with every other, as if the entire crystal shares a single heartbeat. This collective behavior hints that time's flow might emerge from vast networks of quantum interactions, like the ticking of a cosmic clock built from entangled particles. The implications ripple far beyond the lab. If time crystals can sustain their rhythms without energy, could they unlock new ways to build quantum computers, devices where information isn't stored in static bits, but in pulses of time itself? Some researchers even speculate that time crystals might model how time behaves near black holes or in the early universe, where gravity and quantum mechanics collide. They're not just curiosities, they're windows into the edge of time, where the ordinary rules dissolve and the universe's deepest symmetries peek through. Yet the most tantalizing possibility is this: time crystals might show us that time isn't fundamental at all. Just as temperature emerges from the jostling of atoms, perhaps time arises from something deeper, a quantum symphony we're only beginning to hear. Every oscillation of a time crystal is a note in that symphony, a clue that the universe doesn't just keep time, it is time, woven from the same entangled threads that stitch reality together. The Big Bang paints a vivid picture of time's origin, a fiery burst where space, matter, and time itself exploded into existence. But what if that moment wasn't the true beginning, just a turning point in a much larger story? Imagine tracing time backward like a film reel, only to find that before the Big Bang, the cosmic projector wasn't off, it was playing a different movie altogether. Quantum mechanics throws a wrench into our classical intuition, suggesting that even at time's supposed edge, the universe might not have been a singular point but a frothing sea of possibilities. Take the concept of quantum fluctuations, tiny, unpredictable ripples in the fabric of reality that can spawn particles from nothingness. If these fluctuations existed before the Big Bang, they could have nudged the universe into being without a clean starting line. It's like trying to pinpoint where a cloud begins. The closer you look, the more the boundary dissolves. Some theories even propose that time didn't emerge from nothing but transitioned from a timeless state, a phase where cause and effect didn't apply, and the very idea of before loses meaning. Then there's the mind-bending idea of a cyclic universe, where time loops back on itself like an Ouroboros eating its tail. In this model, the Big Bang wasn't a singular birth, but the latest rebound in an endless cycle of expansion and contraction. Picture a cosmic accordion breathing in and out across eons, with each collapse not ending time but resetting it. The discovery we've been exploring forced physicists to grapple with these possibilities, not as abstract thought experiments but as measurable realities. One of the most radical proposals comes from loop quantum gravity, which suggests that time might be stitched together from discrete, indivisible threads like frames in a film strip. At the universe's smallest scales, these frames could blur or even reverse, meaning time's arrow might not always point forward. Experiments with quantum entanglement hint at this flexibility, showing particles influencing each other in ways that seem to defy linear chronology. So where does that leave the edge of time? It might not be a sharp boundary at all, but a shimmering threshold where our classical intuitions break down and quantum weirdness takes over. The deeper we probe, the more time resembles not a straight line, but a tapestry woven from threads we're only beginning to untangle, and the most humbling realization that the question of time's origin might be inseparable from the mystery of existence itself. If our universe is just one page in an infinite cosmic library, what does that mean for time's edge? Multiverse theories flip the script on everything we thought we knew, suggesting that time might not have a single boundary but countless variations, each universe in the grand tapestry writing its own rules. Picture a vast forest where every tree grows at a different pace, some bending in strange shapes, others frozen in perpetual winter. That's the landscape of the multiverse, a place where time could flow backward in one reality, loop endlessly in another, or not exist at all in dimensions beyond our comprehension. The idea isn't just speculative fiction. Quantum mechanics already shows us that particles can exist in multiple states until observed, a phenomenon called superposition. Scale that up to the cosmic level, and you get the many worlds interpretation, where every quantum decision spawns a new universe. In this view, the edge of time isn't a fixed horizon but a branching river, splitting into infinite tributaries with every possible outcome. One universe might have time ending in a fiery big crunch, while another stretches into eternal silence. Some could even exist outside time entirely, like static paintings in a gallery of realities. String theory takes this further, proposing that alternate timelines might vibrate at different frequencies in hidden dimensions. Imagine time as a piano key. Our universe experiences one note, while others resonate with harmonies we can't hear. In some of these realms, time's arrow might not point forward but spiral inward, or fray into threads like a rope unraveling. The discovery that reshaped how we measure time suddenly becomes relative. What's true for our cosmos might be meaningless elsewhere. But the real shocker, these alternate timelines could be closer than we think. Some models suggest that bubble universes with different physical laws might constantly bud off from our own, separated by thin membranes of space-time. If a neighboring bubble had weaker gravity, time there could flow faster, making their civilizations rise and fall in what we'd perceive as an eye blink. Or consider black holes. Their singularities might not be dead ends but gateways to other universes where time runs backward, like a video played in reverse. The implications are staggering. If time's edge isn't universal, then our entire history from the Big Bang to the present might be just one version of events scribbled in a book with infinite blank pages. It challenges the very notion of now, suggesting that every moment we experience is mirrored elsewhere with subtle or drastic differences. And here's the twist. If multiverses exist, our most precise atomic clocks might not be measuring time's fundamental nature, just its local dialect in this particular cosmic neighborhood. Yet for all its grandeur, the multiverse idea isn't without controversy. Critics argue it's untestable, more philosophy than physics. But recent advances in quantum computing and cosmic microwave background analysis are hunting for fingerprints of other universes, subtle statistical anomalies, or gravitational echoes that could hint at collisions with neighboring realities. Even if we never visit these alternate timelines, their theoretical existence reshapes our quest to understand time's edge. It's no longer about finding a single boundary, but mapping the borders of an endless frontier where every possibility plays out, and time itself wears infinite faces. Dark matter has always been the universe's silent architect, an invisible hand sculpting galaxies, bending light, and holding the cosmos together with its gravitational grip. But what if its influence runs deeper than shaping space? What if it's also quietly warping time itself? Picture a river flowing through an unseen landscape. Dark matter's gravitational currents could be twisting that river's path, slowing or speeding time in ways so subtle we've only just begun to notice. This isn't science fiction. It's the startling implication of recent discoveries that link dark matter to time's very fabric. For decades, dark matter was the ghost in the cosmic machine, detected only by the way it tugged on stars and galaxies. Then came the breakthrough. Ultra-precise atomic clocks placed in orbit began picking up strange, microscopic discrepancies in timekeeping. In regions where dark matter's gravitational pull was stronger, time didn't just march forward, it stuttered, as if dragged by an invisible weight. These anomalies were tiny billionths of a second over years, but they matched theoretical predictions that dark matter's gravity could locally distort time, creating pockets where clocks tick at different rates. The implications rewrite the rules of timekeeping. If dark matter bends time, then our most accurate clocks aren't just measuring seconds, they're mapping the hidden contours of the universe's missing mass. Imagine a future where time itself becomes a tool for dark matter detection, with networks of quantum clocks acting like sonar pings echoing through the cosmic dark. Already, experiments are underway to place atomic clocks in satellites at varying distances from Earth's gravity well, hunting for time warps that could reveal dark matter's distribution with unprecedented precision. But the real mystery lies in the extremes. Near the heart of galaxies where dark matter is densest, could time slow to a crawl? Could ancient black holes cocooned in dark matter stretch seconds into centuries? The answers might lie in pulsars, the universe's natural timekeepers. These spinning neutron stars emit radio pulses with metronomic regularity, but some show rhythmic glitches that can't be explained by known physics. Could dark matter's time-bending effects be the culprit? The discovery that dark matter influences time isn't just a new chapter in physics, it's a paradigm shift. Time isn't just a backdrop to the universe, it's a dynamic canvas painted with strokes we're only beginning to see. And as we peer deeper into the dark, we might find that the most elusive substance in existence isn't just shaping the cosmos, it's rewriting the clock. Neutrinos are the universe's quietest witnesses, particles so ghostly they pass through entire planets like moonlight through glass. Born in the hearts of stars, the fury of supernova, and even the Big Bang itself, these nearly massless messengers carry secrets from the farthest edges of time. While light gets scattered, absorbed, or bent by cosmic obstacles, neutrinos travel unimpeded, their paths tracing back to events so ancient that the universe was still in its infancy. That's why detecting them isn't just particle physics, it's time travel. Every neutrino that reaches Earth is a telegram from the past, untouched by the billions of years it spent crossing the void. The real breakthrough came when scientists realized these elusive particles could rewrite cosmic history. Take the relic neutrinos from the Big Bang, still drifting through space like echoes of creation. They're a snapshot of the universe just 1 second old, a time when protons and neutrons were still forming in the primordial plasma. By studying their energy signatures, researchers found something astonishing. These neutrinos move slightly slower than light, their tiny mass acting like a fingerprint of the universe's earliest conditions. It's as if we've been handed a stopwatch from the moment time itself began ticking. But neutrinos didn't just illuminate the past, they exposed gaps in our understanding of time's flow. In 2018, an experiment in Antarctica made headlines when a single high-energy neutrino was traced back to a distant blazar, a supermassive black hole spewing jets of radiation. The twist: the neutrino arrived precisely when telescopes detected a flare from the blazar, proving these particles could synchronize with light across 4 billion light-years. This wasn't just a cosmic coincidence. It was evidence that neutrinos might be threading together cause and effect across unimaginable distances, stitching time's fabric in ways Einstein never predicted. The deeper mystery lies in how neutrinos oscillate, changing flavors between electron, muon, and tau as they travel. This quantum shuffle suggests that time at the smallest scales isn't a steady current but a flickering phenomenon, where particles exist in multiple states until observed. Some theorists even propose that neutrino oscillations could hint at extra dimensions, where time behaves differently beyond our perception. Imagine a clock whose hands sometimes vanish into another realm, only to reappear ticking at a different rate. Now, experiments like Japan's Super Kamiokande and the upcoming Deep Underground Neutrino experiment are pushing further, hunting for neutrinos from supernovae so old their light faded eons ago. Each detection is like finding a fossilized ripple in time, a clue to how the universe transitioned from a seething plasma to the structured cosmos we know. And here's the wildest part: if we can capture neutrinos from the Big Bang itself, we might finally glimpse what happened before time had meaning, when the laws of physics as we know them were still writing themselves. What makes neutrinos so revolutionary isn't just their silence, but their stubborn refusal to play by classical rules. They don't just carry messages from time's edge, they are time's edge, whispering the universe's oldest stories to anyone patient enough to listen. And with every new detection, we're not just measuring seconds or years, we're piecing together the biography of reality itself. If our reality is a simulation, then time might not be the bedrock of existence, just a line of code in some cosmic program. This isn't just wild speculation. It's a hypothesis that has gained serious attention from physicists and philosophers alike. The idea hinges on a simple but staggering question. If advanced civilizations could one day create simulations indistinguishable from reality, how do we know we're not already inside one? And if we are, then time as we experience it, the steady march of seconds, the unshakable arrow from past to future, could be nothing more than a carefully rendered illusion, a variable tweaked by whatever intelligence designed this universe. Think of it like a video game. In a virtual world, time isn't an intrinsic force. It's a parameter set by the game's engine, dictating how fast characters move, how quickly day turns to night. The game might simulate centuries in minutes or freeze time altogether with the press of a button. Now scale that up to our universe. If time is programmed, then phenomena like relativity, where gravity bends time's flow, might not be fundamental laws, but deliberate features coded into the simulation's rules. Even the edge of time, the Big Bang, could be less like a beginning and more like a system boot-up sequence. The implications ripple through every corner of physics. Quantum mechanics already suggests reality isn't fixed until observed, a glitch that makes eerie sense if the universe runs on processing power, rendering details only when needed. Black holes, with their infinite density and frozen time, might be more like buffer zones where the simulation conserves resources, and those tiny irregularities in atomic clocks. They could be the equivalent of frame rate drops, moments when the system struggles to keep up with its own calculations. But here's where it gets truly mind-bending. If time is a construct, then the discovery that reshaped how we measure it, the realization that it's elastic, granular, perhaps even emergent, might be evidence of something deeper. The universe's underlying code could have limits, a resolution beyond which time can't be divided, just as a pixel can't display half a color. Some theorists argue that the Planck length and Planck time, the smallest meaningful units of space and duration, are the simulation's native pixel size, the smallest steps its processor can handle. Critics dismiss this as untestable metaphysics, but supporters point to oddities in quantum experiments that resemble optimization shortcuts, entangled particles communicating instantly across distances. That's not spooky action at a distance, it's two objects sharing the same memory address in the cosmic RAM. Even the holographic principle, with its suggestion that reality is a projection from a two-dimensional surface, fits neatly into the simulation analogy, like a 3D game rendered from flat textures. The most unsettling possibility, that time's edge isn't a boundary at all, but a buffer overflow, a glitch where the simulation resets or crashes. If that's true, then our quest to measure time isn't just science, it's reverse engineering the universe's source code, hunting for clues in the static between seconds. And whether we're in a simulation or not, one thing becomes clear: time, as we know it, is far stranger than we ever imagined. The first gravitational wave ever detected wasn't just a ripple in space, it was a tremor in time itself. When LIGO lasers flickered in September 2015, the signal they captured told a story older than humanity. Two black holes, locked in a death spiral over 1 billion years ago, warping spacetime so violently that their collision sent shockwaves racing across the cosmos at light speed. But hidden in those faint vibrations was something even more profound, a direct measurement of how time bends under gravity's crushing grip. As the black holes spiraled closer, their gravitational dance stretched and compressed not just space, but the very fabric of time around them, creating fluctuations so precise they matched Einstein's predictions down to the millisecond. What made this discovery revolutionary wasn't just confirming relativity. It was the way gravitational waves exposed time's malleability in real cosmic events. Unlike lab experiments with atomic clocks or satellite tests, these waves carried fingerprints from regions where gravity is so intense that time slows to a near standstill. The final milliseconds before the black holes merged revealed time's distortion at its most extreme, with each orbit compressing years into microseconds. It was as if the universe had handed us a slow-motion replay of time itself unraveling. But the real surprise came when scientists compared gravitational wave data with traditional electromagnetic observations. When neutron stars collided in 2017, telescopes detected the explosion's light arriving slightly later than the gravitational waves, not because light was slower, but because time flowed differently along the two paths. The gravitational waves slipped through warped spacetime like fish through a current, while light had to navigate the bends, proving that time isn't just curved by gravity, it's textured with wrinkles that change how information travels. Now, gravitational wave astronomy is rewriting the rules of timekeeping. New detectors like LISA will soon track collisions with such precision that they could reveal if time behaves differently near supermassive black holes, where some theories predict it might loop or fracture. Others hunt for primordial waves from the Big Bang, which could carry imprints of time's very first ticks. Every new detection isn't just adding to our map of the cosmos, it's testing whether time's edge is a boundary or a doorway, and what might lie beyond. The arrow of time has always seemed as certain as gravity, an unstoppable river flowing from past to future, carrying everything from dying stars to melting ice cream toward greater disorder. For over a century, physicists pointed to entropy as the engine behind this one-way street, the reason we remember yesterday but not tomorrow. The second law of thermodynamics, with its ironclad rule that disorder must increase, seemed to etch time's direction into the fabric of reality itself. But what if entropy is just a symptom of something deeper, a shadow cast by quantum processes we're only beginning to understand? Recent experiments have cracked open a tantalizing possibility that time's arrow might be rooted in the quantum world's peculiar symmetries. Take the behavior of entangled particles, which remain mysteriously linked across vast distances. When one particle's state is measured, its partner instantly responds, a phenomenon that appears to defy classical notions of cause and effect. Stranger still, some quantum systems seem to evolve equally well forward or backward in time, like a movie that makes sense whether played normally or in reverse. This symmetry hints that at the smallest scales, time's arrow might not be fixed at all. So why does time flow forward in our everyday experience? The answer may lie in how quantum decoherence, the process by which quantum systems interact with their environment, breaks these symmetries. Imagine a drop of ink spreading in water. At the molecular level, each collision between ink and water molecules is reversible, but statistically, the ink will almost always disperse. Similarly, while individual quantum events might be time-symmetric, their collective behavior in complex systems like our brains or the cosmos tips the scales irreversibly toward entropy's rise. But here's where the discovery reshuffles the deck. Certain quantum systems, like those in ultra-cold laboratories, have been caught violating this expected flow, exhibiting negative entropy behaviors where disorder temporarily decreases. It's as if time's arrow stutters, wobbling backward for fractions of a second before resuming its usual course. These anomalies suggest that entropy isn't the sole dictator of time's direction. It's more like a conductor trying to herd quantum musicians who occasionally play their own tune. The implications ripple across physics. If time's arrow isn't absolute, could pockets of the universe exist where it points sideways or loops back on itself? Some theories propose that the Big Bang's low entropy state wasn't a beginning but a fluctuation in an eternal cycle, like a bubble forming in boiling water. Others speculate that black holes might host regions where entropy runs in reverse, effectively creating islands of backward time in the cosmic sea. What emerges isn't just a new layer to time's mystery, but a radical rethinking of causality itself. The universe might not have a single timeline so much as a braided river, with quantum threads occasionally twisting against the current. And the most humbling realization, that our perception of time's relentless forward march could be the result of our own limitations, like fish mistaking the river's flow for the ocean's entirety. Time travel has long been the playground of science fiction, from H.G. Wells' Victorian time machine to Hollywood's flashy DeLoreans. But what if the boundary between fantasy and physics isn't as solid as we think? The same discovery that revealed time's quantum granularity also cracked open a backdoor in Einstein's equations, one where wormholes, those hypothetical cosmic shortcuts, could theoretically connect distant moments as easily as distant places. Picture a tunnel where one mouth ages at Earth's pace while the other hurtles near a black hole, its time slowed to a crawl. Step through, and you might emerge centuries in the past, or so the math suggests. Yet the devil is in the quantum details. Wormholes, if they exist, would be riddled with paradoxes. Imagine sending a clock through one only to have it return before you sent it, like a cosmic version of mailing yourself a letter that arrives yesterday. This isn't just a brain teaser, it's a violation of causality that makes physicists recoil. Quantum mechanics offers a bizarre solution. Wormholes might only stay open if threaded with exotic matter, a hypothetical substance with negative energy that defies gravity's pull. Even then, calculations suggest these time tunnels would snap shut faster than a mousetrap, crushed by the very granularity that makes time measurable in the first place. Cosmic strings' theoretical flaws in space-time left over from the Big Bang present another tantalizing path. These ultra-dense filaments, thinner than an atom but stretching across galaxies, could warp time around them like a twisted telephone cord. Two strings moving past each other at near light speed might create closed time-like curves, loops where time circles back on itself. The catch: you'd need strings with the mass of entire stars packed into each inch, and even then, the quantum jitter of time's smallest units could destabilize the loop before you could take a single step into yesterday. The wild card in all this is quantum entanglement, where particles instantly influence each other across space. Some interpretations suggest this spooky action might also work across time, with measurements today affecting particles in the past. Laboratories have already demonstrated this retrocausality in tightly controlled experiments, proving that at the quantum level, time's arrow isn't always straight. But scaling this up to human scales would require harnessing phenomena we barely understand, like somehow entangling every particle in your body with their future or past selves. What emerges isn't a rejection of time travel's possibility, but a roadmap littered with quantum speed bumps. The universe seems to allow time bending in its rulebook, then scribbles in footnotes that make it nearly impossible to execute. Yet for all the hurdles, the mere fact that physics entertains the idea at all is a testament to how deeply our understanding of time has evolved. The edge of time isn't a wall, it's a maze with paths that twist in ways we're only beginning to trace. What if the flow of time isn't just a feature of the universe, but a trick of the mind? This provocative idea turns conventional physics on its head, suggesting that without consciousness, time might not flow at all. Think of it like a movie projector. The film exists frame by frame, but it's only when light hits the reel and an observer watches that the illusion of motion emerges. In this view, the universe could be a vast, timeless landscape where consciousness stitches together moments into what we experience as duration. The discovery that time is granular and malleable at quantum scales lends eerie support to this notion. If time's smallest units flicker unpredictably, how does our brain weave them into a seamless narrative? Neuroscience offers clues. Our perception of time isn't a passive recording but an active construction, shaped by attention, memory, and even emotion. Ever noticed how time drags during a dull lecture but vanishes on a thrilling vacation? That's your brain editing reality in real time. Experiments with psychedelics and brain injuries reveal even stranger distortions, patients reporting moments stretched into eternity or decades compressed into instants. These aren't just glitches, they're proof that time as we know it is a carefully curated illusion, sculpted by neural processes. Quantum mechanics deepens the mystery. In the famous double-slit experiment, particles behave as waves until observed, as if reality hesitates to commit until a conscious mind looks. Some interpretations, like the von Neumann-Wigner hypothesis, take this further, proposing that consciousness collapses quantum possibilities into definite outcomes. If observation shapes reality at the smallest scales, could it also orchestrate time's flow? The discovery of time's quantum granularity makes this less outlandish, like finding the universe has a render settings menu where consciousness selects the frame rate. Yet the implications unsettle even seasoned physicists. If consciousness anchors time's flow, does time stop for unobserved parts of the universe? Could alternate timelines exist in superposition until a mind chooses one? The debate splits academia. Some argue consciousness is a bystander in a deterministic cosmos, while others see it as the loom weaving time's fabric. What's undeniable is that the more we probe time's edge, the more it seems entangled with perception, a dance of observer, and observed where the steps themselves might be an invention of the dancers. Here's where the discovery delivers its sharpest twist. If time's flow emerges from consciousness interacting with quantum reality, then black holes and the Big Bang aren't just physical events, they're chapters in a story whose narrator might be us. The universe could be less a clockwork mechanism and more a grand collaborative art project, with each conscious observer brushing strokes onto the canvas of time. And that raises a question far stranger than how we measure time, whether we're measuring it at all or creating it moment by moment. Quantum computers don't just crunch numbers, they dance with time itself. At their core are qubits, particles that exist in superposition, spinning in multiple states at once like cosmic acrobats defying gravity. This isn't just parallelism. It's as if every possible calculation unfolds simultaneously across branching timelines, each qubit a thread in a tapestry of alternate realities. When researchers first harnessed this phenomenon to simulate time's edge, they weren't just building faster computers. They were constructing portals to realms where the rules of causality bend like light around a black hole. Take, for example, Google's quantum processor Sycamore. In 2019, it solved a problem in minutes that would take classical supercomputers millennia, not by brute force, but by leveraging superposition to explore countless solutions at once. The real breakthrough came when physicists realized this wasn't just about speed. By tweaking qubits to mimic quantum systems evolving backward or forward in time, they could recreate conditions near singularities or the Big Bang, environments too extreme for any lab to physically replicate. It's like using a kaleidoscope to model the birth of a universe. Each twist of the qubits reveals a new fractal edge of time's behavior, the most startling revelation. Quantum computers exposed cracks in our classical notion of time's arrow. In one experiment, researchers programmed qubits to simulate particles interacting across time loops, where cause and effect circle back like a snake eating its tail. Shockingly, the system didn't collapse into chaos, it stabilized, suggesting that at quantum scales, time might not flow linearly at all. These simulations hinted that what we perceive as time's relentless forward march could be an emergent property, like temperature arising from atomic motion, rather than a fundamental feature of reality. Now, quantum computers are probing even wilder frontiers. Some teams are simulating hypothetical chronon crystals, structures where qubits oscillate in patterns that echo the granular nature of time itself. Others are modeling wormholes by entangling qubits across vast distances, creating corridors where information seems to teleport, effectively skipping through time. The implications ripple beyond physics. If time's flow is computable, could we one day debug it, find glitches in the cosmic code? The line between simulation and reality blurs when your computer doesn't just calculate time, it plays with its building blocks. Yet for all their power, quantum computers also highlight time's stubborn mysteries. Decoherence, the fragile collapse of superposition, acts like a quantum hourglass, limiting how long these timelines can branch before collapsing into a single outcome. It's a reminder that even as we peer into time's quantum core, some doors may remain locked, not by technology, but by the universe's own deep rules. What's clear is this: the marriage of quantum computing and time physics isn't just reshaping our tools, it's rewriting our place in the story of existence. The silence of the cosmos isn't just eerie, it's one of the universe's greatest puzzles. On a planet teeming with life, orbiting a star among hundreds of billions, in a galaxy lost in a sea of others, why does the night sky remain so quiet? This is the Fermi paradox in a nutshell, the staggering disconnect between the high probability of alien civilizations and the utter lack of evidence for their existence. But what if the answer isn't about space at all? What if it's hidden in the nature of time itself? The discovery that reshaped how we measure time's edge might hold the key. Consider this: even if intelligent life is common, the universe operates on timescales that dwarf human comprehension. Civilizations could rise and fall in the blink of a cosmic eye, their signals fading into the void before reaching anyone who might listen. Imagine two islands separated not by ocean, but by epochs, one culture sending smoke signals long after the other has turned to dust. The granular, quantum nature of time adds another layer. If cosmic signals are constrained by time's smallest units, like a radio broadcast chopped into fragments, they might dissolve into noise before crossing the interstellar gulf. Then there's relativity's cruel twist. A civilization near a black hole or moving at relativistic speeds would experience time drastically slower than the rest of the universe. Their 1,000-year golden age might pass in what seems like weeks to outsiders. By the time their messages arrive, the senders could be long gone, their transmissions relics of a dead empire. Even if we somehow intercepted their signals, decoding them would be like trying to read a letter from a language that vanished millennia ago. But the most haunting possibility: that the edge of time isn't just a barrier, it's a filter. The universe might be littered with the ruins of civilizations that hit a wall, not of resources or technology, but of time's fundamental limits. Perhaps no society can survive the quantum decoherence of entropy forever, or navigate the fractal branching of multiverses where every decision splinters reality. The silence out there might not mean we're alone, just that we're all prisoners of time's relentless current, separated not by light years, but by the irreversible flow of moments we can't share. Yet there's hope in the paradox. If time's edge is malleable, as quantum experiments suggest, then advanced civilizations might have found ways to stitch together its fraying threads, using black holes as time capsules or entanglement as a cosmic telegraph. Their absence could be an illusion, their presence hidden in the quantum static between seconds. The universe's silence isn't empty, it's a symphony we're only beginning to hear, played on instruments tuned to the rhythm of time itself. Deep in the cosmic void, hidden behind the dust and stars of our own Milky Way, lies a gravitational enigma so powerful it's dragging entire galaxies toward it at millions of miles per hour. Astronomers call it the Great Attractor, an invisible titan with the mass of tens of thousands of Milky Ways, bending the paths of galaxies like a cosmic whirlpool. But its influence might stretch far beyond tugging on stars and gas. The same gravitational might that pulls galaxies could be twisting the very fabric of time around it, creating pockets where clocks tick slower and the edge of time itself stretches like taffy. Picture a river flowing toward a waterfall. Near the edge, the current accelerates, dragging everything with it, but the water closest to the falls moves slower, trapped in the whirlpools at the brink. The Great Attractor could be doing something similar with time. Galaxies falling toward it would experience time dilation, their clocks running slightly slower than those in quieter cosmic backwaters. This isn't just theoretical. Observations of galaxy clusters near the attractor show subtle distortions in their light-stretched wavelengths that hint at time itself being warped by the region's immense gravity. The real breakthrough came when scientists mapped these distortions against models of general relativity. The math revealed something startling. The Great Attractor isn't just a static pit in space-time. It's a dynamic engine, its gravitational field fluctuating as more matter falls into its grasp. These fluctuations create ripples in time's flow, like a pond disturbed by rain. In regions where the ripples overlap, time might stutter, advancing in fits and starts rather than a smooth stream. It's as if the universe has a heartbeat, and the Great Attractor is its muffled drum. What makes this discovery revolutionary isn't just the scale of the effect, but what it reveals about time's edge. If colossal structures like the Great Attractor can warp time locally, could even larger cosmic formations like the mysterious dark flow of galaxies moving toward some unseen horizon be bending time on scales we can't yet measure? The implications rewrite our understanding of the cosmic clock. Time might not flow uniformly across the universe but ripple and pool like water in a bumpy basin, with some regions aging faster while others linger in slow motion. Yet the Great Attractor holds its secrets close. Hidden behind the Milky Way's dusty disk, it resists direct observation. Even our best X-ray and radio telescopes struggle to pierce the veil. Some theorists speculate it's not a single object but a knot in the cosmic web, where filaments of dark matter converge to form a gravitational nexus. Others wonder if it's a sign of something even stranger, a flaw in space-time left over from the Big Bang, a cosmic scar where the rules of physics twist in ways we're only beginning to glimpse. One thing is certain, the Great Attractor isn't just pulling galaxies. It's pulling at the boundaries of our understanding, forcing us to rethink time's nature on the grandest scales. And as we peer deeper into its hidden heart, we might find that the edge of time isn't a fixed line but a shifting frontier, one that bends, breathes, and flows with the universe's darkest currents. Time isn't just a backdrop for life, it's the unseen sculptor shaping its possibilities. If time flows differently across the cosmos, as relativity and quantum discoveries suggest, then alien civilizations might not just exist in distant galaxies, but in entirely different temporal landscapes. Imagine a planet orbiting a black hole, where one Earth year stretches into centuries. Life there would evolve at a glacial pace, its civilizations rising and falling in what we'd perceive as a single human lifetime. Or consider a rogue planet hurtling through space at near light speed, its inhabitants experiencing time so compressed that their entire technological revolution flashes by in our cosmic blink. These aren't just thought experiments, they're real consequences of time's flexibility, forcing astrobiologists to rewrite the rules of where and how to search for life. The discovery that time is malleable shattered the assumption that all life shares the same clock. Traditional searches for extraterrestrial intelligence, like SETI radio telescopes, operate on a human time scale, listening for signals that might take decades or centuries to arrive. But what if the message we're waiting for was sent in pulses lasting microseconds from a planet where time crawls, or stretched into millennia-long drones by a star's crushing gravity? Our detectors might be tuned to the wrong rhythm, missing civilizations speaking in time signatures we can't yet hear. This revelation has sparked a new frontier in astrobiology: temporal habitability. Scientists now model how extreme time dilation could affect life's building blocks. Enzymes on a high-gravity world might catalyze reactions millions of times slower, while DNA on a relativistic spacecraft could experience mutation rates frozen to a near standstill. Even the Fermi paradox, the eerie silence of the cosmos, gets a fresh twist. Advanced civilizations might not be absent. They could be temporally isolated, their signals arriving too fast or too slow for our instruments to recognize. The search strategies are evolving too. Next-generation telescopes like the Square Kilometre Array won't just scan frequencies, they'll hunt for anomalies in signal duration and interval patterns that could betray a non-human sense of time. Meanwhile, quantum communication experiments suggest another possibility. Aliens might not use radio waves at all, but entangled particles linked instantaneously across space and potentially across time. If a civilization mastered quantum timekeeping, their messages might not travel through space as we know it, but exist in a superposition of past and future until observed. The most profound implication: life might not just be rare in space, but in time. Two civilizations could flourish in the same galactic neighborhood, separated not by light years, but by relativistic time warps that make coexistence impossible. The universe could be teeming with intelligence, each strand woven into the cosmic tapestry at its own tempo, forever out of sync. Yet in this temporal mosaic lies hope, that by learning to measure time's edges, we might finally learn to listen across them. The quantum Zeno effect is like hitting pause on reality's remote, but instead of freezing a movie, it halts time itself at the quantum scale. Named after the ancient Greek philosopher's paradox about motion, this bizarre phenomenon reveals that simply observing a particle can trap it in a single state, as if time stops for it. Imagine flipping a coin and catching it mid-air over and over, so rapidly that it never lands. That's essentially what happens when scientists bombard a quantum system with continuous measurements. Each observation resets the system's clock, preventing it from evolving naturally. In labs, this has been used to keep unstable atoms from decaying and photons from changing polarization, effectively creating pockets of frozen time where change is held at bay by the sheer act of looking. What makes this discovery revolutionary isn't just the technical wizardry, it's the philosophical aftershock. If watching a quantum system alters its flow of time, does that mean time's passage isn't an absolute feature of the universe, but something that emerges from interaction? The effect blurs the line between the observer and the observed, suggesting that measurement isn't a passive act but a force that shapes reality's tempo. In quantum experiments, particles seem to decide whether to evolve or stand still based on how often they're checked, as if time itself is a conversation between the system and the scientist. This eerie control over time's flow has startling parallels in cosmology. Near black holes, where gravity warps time to a near standstill, the universe might be running its own version of the quantum Zeno effect, freezing infalling matter into eternal slow motion from an outsider's perspective. Even more radical is the idea that conscious observation could play a role in cosmic timekeeping. Some interpretations of quantum mechanics propose that without observers, reality remains in a haze of possibilities, with time's arrow only solidifying when a mind interacts with the system. It's as if the universe needs witnesses to stitch together moments into a coherent timeline. Yet the quantum Zeno effect isn't just a thought experiment, it's a tool reshaping technology. Quantum computers exploit this principle to stabilize qubits, preventing them from decohering by frequently measuring their states. In medicine, researchers are exploring how similar effects might slow biochemical reactions, potentially pausing cellular damage long enough for interventions. These applications hint that time's edge isn't just a frontier to study, but a dial we might one day turn. The deepest mystery, that time's flow, which feels so inexorable in our daily lives, could be as fragile as a house of cards at the quantum level. The quantum Zeno effect doesn't just challenge how we measure time, it asks whether time exists independently at all, or if it's a tapestry woven from countless acts of observation. Every flicker of a stabilized atom whispers that the universe's clock might not tick on its own, but only when something or someone is listening. The Planck time isn't just a number, it's a boundary where our understanding of reality unravels. At 10 to the minus 43 seconds, this unimaginably brief interval marks the smallest slice of duration physics can meaningfully describe. To grasp just how fleeting this is, consider a single second compared to the age of the universe, about 13.8 billion years. Now divide that second by a number so large it dwarfs all the atoms in the observable cosmos. That's the scale we're dealing with, a realm where time itself might dissolve into something far stranger. The discovery that time could be quantized at this scale sent shockwaves through physics. Think of it like a cosmic pixel. Just as a digital image breaks down into tiny squares when you zoom in far enough, time might fracture into indivisible Planck-sized chunks at its most fundamental level. This revelation didn't just tweak equations, it forced scientists to confront the unsettling idea that time's smooth flow is an illusion, a kind of cosmic sleight of hand masking its true granular nature. Why does this matter? Because if time is pixelated, then concepts like before and after take on new meaning at the Planck scale. Imagine flipping through a flipbook so fast the pages blur into motion. Our experience of time's continuity might work the same way, with Planck moments flickering by too quickly for any clock to catch. This granularity could explain some of quantum mechanics' weirdest quirks, like how particles seem to teleport between states without traversing the middle ground. If time advances in tiny hops, then at the smallest scales, cause and effect might not unfold smoothly but in sudden quantum leaps. But the real mind-bender is what lies beyond the Planck time. Current physics hits a wall here, a point where gravity becomes so strong and quantum fluctuations so wild that space and time lose their familiar shapes. Some theories suggest that at this edge, time might not even exist as we know it, replaced by a frothing quantum foam where past, present, and future churn unpredictably. It's as if the universe has a refresh rate, and below Planck time, the screen flickers into static. The implications ripple outward. If time is quantized, then black holes where gravity stretches time to near standstill might be places where this granularity becomes visible, like grains of sand caught in cosmic hourglass. The Big Bang's first moments wouldn't be a smooth expansion, but a rapid-fire sequence of Planck time ticks, each one a quantum leap in the birth of reality. Even our perception of free will comes into question. If the universe updates in discrete steps, are our choices made in the gaps between Planck moments? Yet for all its strangeness, Planck time isn't just theoretical. Experiments with ultra-fast lasers and quantum vibrations are hunting for evidence of this granularity, looking for tiny hiccups in time's flow that might betray its pixelated nature. The discovery we're exploring didn't just redefine time's edge, it opened a door to a deeper layer of existence, one where the universe itself might be running on a quantum clock we're only beginning to hear tick. The universe's final act might not be a dramatic explosion or a sudden collapse, but a slow, silent fade to black. This is the chilling prophecy of heat death, a fate where time itself loses all meaning. Picture a cosmos so vast and empty that galaxies have long since burned out, black holes evaporated into whispers of radiation, and even the fabric of space has stretched into an infinite, featureless void. In this distant era, the temperature everywhere would approach absolute zero, a state of perfect equilibrium where no energy flows, no stars ignite, and no change occurs. Time, in any meaningful sense, would cease to exist not because it stops, but because there's nothing left to measure it with. No clocks, no light, no observers, just an eternal stillness where the universe's final flicker of heat dissipates into darkness. Yet there's another contender for time's ultimate edge, one far more violent. The Big Crunch is the cosmic mirror of the Big Bang, a scenario where gravity finally wins its eons-long tug of war with expansion. Imagine all the galaxies now hurtling apart, suddenly reversing course like a rewinding film. Space itself would contract, temperatures soaring as matter piles onto matter, compressing into an inferno denser than any star. Time, warped by this crushing gravity, would speed up in the final moments, a frantic countdown to singularity. The final instant would be a mirror of the Big Bang's first, a state of infinite density where the laws of physics break down, and time's arrow shatters into fragments too small for even quantum theory to describe. The discovery that reshaped our understanding of time's edge revealed something startling. Both scenarios hinge on the universe's hidden architecture. Heat death assumes dark energy keeps accelerating expansion indefinitely, while the Big Crunch requires gravity to eventually overpower it. But here's where things get strange. Quantum fluctuations near the end of time could rewrite the rules entirely. In a heat-death scenario, quantum tunneling might allow random bubbles of new universes to spontaneously form in the void, a cosmic resurrection where time reboots in isolated pockets. Conversely, a collapsing universe might not end in a singularity but bounce, a Big Crunch birthing a new Big Bang in an endless cycle, the most haunting possibility. That time's edge isn't a single event but a spectrum of endings. Some regions of the universe might collapse while others freeze, like a dying fire with embers flickering out at different moments. The discovery that time is granular and quantum in nature suggests that even the end could be fragmented, a mosaic of final instants, each playing out in its own isolated pocket of reality. The true fate of time might not be a question of or, but, and a cosmic epilogue written in many languages, each incomprehensible to the other. Time isn't just a feature of reality, it might be the stage itself, woven into the very script of existence. For centuries, we assumed time was a fundamental backdrop, an unchanging river flowing through the universe. But the discovery that shattered traditional timekeeping revealed something far stranger. Time could be an illusion, emerging from deeper quantum processes like warmth emerging from the motion of atoms. Think of a movie screen. What we perceive as time's smooth flow might just be the flicker of countless quantum interactions, each too small and fast to see individually, but together creating the illusion of continuity. This idea turns classical physics on its head. If time isn't fundamental, then what we call now might be no more real than the colors in a rainbow, a phenomenon created by our limited perspective. Some theories, like loop quantum gravity, propose that time arises from the entanglement of quantum particles, a cosmic network of relationships that creates the appearance of sequence. Picture a vast crowd doing the wave in a stadium. No single person moves through time, but the collective motion gives rise to a traveling ripple. Similarly, time's flow could be the collective behavior of countless quantum events, with no single clock driving it. The implications ripple through cosmology. If time is emergent, then the Big Bang wasn't just the beginning of our universe. It might have been the moment time itself crystallized from a timeless quantum foam. Near black holes where gravity stretches time to a standstill, we could be glimpsing regions where this emergence unravels, revealing the timeless substrate beneath. Even our everyday experience of cause and effect comes into question. Without time as a fundamental scaffold, the chain of before and after might be a shorthand for something far more intricate, like quantum probabilities resolving into the stories we tell ourselves. Yet the most radical possibility is this: if time emerges from deeper laws, then those laws might operate outside time entirely. The universe's underlying code could be a timeless matrix, with our experience of duration akin to a character in a video game believing they're moving through a story, unaware the entire narrative exists simultaneously in the program's memory. Experiments with quantum entanglement already hint at this, particles influencing each other instantaneously, as if the universe is processing relationships all at once, and time is just the order we perceive them in. What emerges isn't just a new theory of time, but a new way to see reality. The edge of time isn't a boundary, it's a threshold where the universe's deepest layers peek through, hinting that every moment we experience is a note in a symphony we're only beginning to hear. And the most humbling thought, that time might not be the conductor of that symphony, but one of its instruments. The human brain is a master illusionist, stitching together the flickering frames of sensory input into what feels like a seamless, unbroken present. We experience time as a smooth river, flowing steadily from one moment to the next, yet the discovery that time's edge is granular at the quantum level reveals a staggering disconnect. Our perception isn't just incomplete, it's a carefully constructed fiction, a trick of the mind that hides the fragmented truth of reality. Neuroscience uncovers how this illusion works. Every thought, every sensation we perceive as now is actually a delayed reconstruction, a best guess assembled by the brain from scattered electrical signals. Imagine watching a movie where each frame arrives slightly out of order, yet your brain edits it into coherence before you even notice. That's what happens every millisecond. Visual, auditory, and tactile inputs arrive at different speeds, but the brain synchronizes them into a single moment. This temporal binding window, typically lasting a tenth of a second, is why we don't perceive the lag between a lightning strike and thunder, or the infinitesimal gaps in time's quantum fabric. Yet the brain's smoothing effect can't account for the deeper strangeness revealed by quantum mechanics. At the smallest scales, time doesn't flow, it stutters, advancing in discrete hops like frames in a cosmic film strip. Some theories suggest consciousness itself might emerge from these quantum jumps, with each moment of awareness corresponding to a new frame rendering in the mind. Experiments with psychedelics and brain injuries support this. When neural processing is disrupted, people report time fracturing, experiencing moments as disjointed snapshots or stretched into eternity. It's as if the curtain slips, revealing the raw, unedited footage beneath our polished perception. The dissonance between how we experience time and its true nature raises profound questions. If reality refreshes itself in quantum increments, does free will exist in the gaps between frames? Could meditation or technology one day let us perceive time's granularity, like seeing the flicker of an old movie projector? The discovery that time's edge is fragmented doesn't just challenge physics, it forces us to rethink what it means to be present at all. Perhaps the flow of time isn't something we observe, but a story the brain tells to make sense of a universe far stranger than we ever imagined. Salvador Dali's melting clocks in the persistence of memory aren't just surrealist oddities, they're a visceral protest against time's rigidity. Those drooping timepieces, draped over barren landscapes like wet rags, capture what scientists would later confirm. Time isn't a rigid metronome but a fluid, malleable force. Dolly painted his masterpiece in 1931, decades before atomic clocks proved time's elasticity under gravity, yet his intuition mirrored relativity's revelations. Art, it seems, had already sensed what science would laboriously measure, that time bends, warps, and sometimes, like those clocks, loses its shape entirely. Philosophers, too, have danced around time's edges long before quantum mechanics gave them a vocabulary. Martin Heidegger argued that time isn't just a sequence of events, but the very fabric of human existence, a tapestry where past, present, and future intertwine. His idea of Dasein, or being in the world, posits that we don't merely move through time, we are time, shaped by its flow and haunted by its limits. It's a notion that eerily resonates with modern physics, where time emerges from quantum relationships rather than existing as an independent backdrop. Heidegger's existential musings and the discovery of time's granularity share a common thread. Time isn't out there, separate from us. It's woven into our perception, our choices, even our atoms. Literature has its own lexicon for time's paradoxes. In 100 Years of Solitude, Gabriel Garcia Marquez bends time like a rubber band, compressing generations into overlapping cycles where the past echoes relentlessly in the present. The novel's Macondo isn't just a town, it's a temporal labyrinth where prophecies fulfill themselves and history repeats like a broken record. Marquez's magic realism, dismissed as fantasy when published in 1967, now reads like a poetic premonition of multiverse theories where alternate timelines might coexist in quantum superposition. Even music bends time to its will. A composer like Arvo Pärt crafts tintinnabuli pieces where notes stretch and contract, creating the illusion that time itself is breathing. His Spiegel im Spiegel mirrors the quantum idea of time's granularity. Each sustained note a discrete chronon, a pixel in the auditory canvas. Listen closely, and you'll hear the silence between the tones, the gaps where time's structure flickers like a candle in the wind. It's no accident that Pärt's works are used in films about space and mortality. They tap into the same awe that grips physicists staring at equations describing time's edge. The discovery that time is quantized didn't just revolutionize labs, it validated centuries of artistic and philosophical speculation. From Van Gogh's starry vortices, which evoke space-time curvature, to Borges' garden of forking paths, where every decision spawns parallel timelines, creativity has always been a silent partner in humanity's quest to unravel time. Science may measure it, but art and philosophy remind us why it matters that time's true mystery isn't in its ticks, but in how it shapes the stories we tell, the beauty we create, and the meaning we desperately try to preserve against its relentless flow. Optical lattice clocks are rewriting the rules of precision, trapping atoms in grids of laser light so exact they could detect a gravitational wave by the way it stretches time itself. Picture thousands of strontium atoms suspended in an interference pattern so fine it resembles a crystal of light, each atom ticking between energy states with near-perfect synchronicity. These aren't just improvements on atomic clocks, they're leaps into uncharted territory, so sensitive they'd lose less than a second over the entire age of the universe. But their real magic lies in what they reveal. Tiny distortions in time's flow caused by Earth's gravity, continental drift, or even dark matter's invisible tug. When researchers at the University of Tokyo compared two optical clocks placed just a foot apart in height, they detected time passing slightly faster for the higher clock, proof that even a small change in gravity's pull alters time's rhythm. Now imagine scaling this up to quantum networks, where entangled clocks across continents could create a global timekeeping web immune to local disturbances. A master clock in space, linked to Earth-based counterparts via quantum satellites, might one day sync everything from GPS to power grids with unprecedented accuracy. But the implications run deeper than technology. Such networks could test whether time itself is universal or fractured. If a clock orbiting a black hole ticks differently than one on Earth, does that mean time's edge shifts with perspective? Experiments already in development aim to place optical clocks on the International Space Station, where microgravity and velocity extremes will stress test relativity like never before. Meanwhile, space-based experiments are pushing further. The European Space Agency's proposed atomic clock ensemble in space would place ultra-precise clocks in orbit, free from atmospheric interference, to map times warping around Earth with microscopic precision. These missions aren't just about better clocks, they're telescopes pointed at time itself, hunting for anomalies that might betray hidden dimensions or quantum gravity effects. Some theorists even suggest that networks of quantum clocks could detect time crystals, exotic phases of matter that oscillate without energy, potentially unlocking new states of time structure. The future of time measurement isn't just about counting seconds more finely, it's about probing the universe's scaffolding. With each leap in precision, we're not just observing time's flow, we're interrogating it, demanding answers about whether it's fundamental or emergent, continuous or stuttering. And as these experiments unfold, they might reveal that the edge of time isn't a fixed horizon, but a frontier that recedes with every question we ask. The discovery that reshaped how we measure time's edge didn't just add a new chapter to physics, it tore up the old textbook entirely. What began as a quest for more precise clocks unraveled into a revelation. Time isn't a steady river, but a stormy sea, churned by gravity, quantum uncertainty, and the very structure of reality itself. From the way black holes stretch seconds into eons, to the eerie stutter of time's quantum grains, every breakthrough has peeled back another layer of mystery, showing us that the universe's clockwork is far stranger than we ever dreamed. This isn't just about science, it's about rewriting our place in the cosmos. For centuries, humans saw time as an unchanging backdrop, a rigid stage where the drama of existence played out. Now we know it's more like a living, breathing character in that drama, bending under the weight of galaxies, flickering at the smallest scales, and perhaps even emerging from something deeper we've yet to name. The implications ripple through everything: how we navigate with GPS, how we study the Big Bang, even how we ponder the fate of the universe. Time's flexibility means the past, present, and future might not be as fixed as they seem. Yet for all we've learned, the most thrilling realization is how much remains unknown. Those flickers in atomic clocks, the way entangled particles seem to dance outside time's flow, the holographic whispers at the universe's edge, they're all clues pointing toward a grander theory waiting to be uncovered. The next generation of experiments, from quantum satellites to space-based gravitational wave detectors, will push further into this frontier, testing whether time is fundamental or illusory, continuous or stitched together from fragments. So where does this leave us on the threshold? Every measurement, every theory, every daring experiment is a step toward understanding not just how time works, but what it truly is. The journey has barely begun, and that's what makes it so exhilarating. Whether you're a scientist, a curious viewer, or someone who's just starting to question the nature of reality, one thing's certain: the story of time is still being written, and the next page could change everything. What do you think lies beyond time's edge? Could it be layers of reality we can't yet see, or something even wilder, Drop your thoughts in the comments. We're all part of this conversation. And if you're hungry for more deep dives into the universe's greatest mysteries, hit that subscribe button. The future of discovery is waiting, and it's going to be